Good afternoon, everybody. I hope the next 45 or 50 minutes of talk about geothermal systems, I hope you'll find them interesting, and that you won't kind of nod off after lunch. So hope you'll quite like it. I'll try and give you a general kind of overview of various aspects to do with geothermal systems and energy from that renewable energy source. But perhaps first start off with a bit about me. I work at the British Geological Survey. Way back in the late 80s, I did a PhD around the geothermal system in Costa Rica. I was looking at high temperature fluid rock reaction and had a very nice time in northern Costa Rica exploring the volcanoes and geothermal areas. I was subsequently employed by the BGS as a geochemist, which is my primary role, especially in laboratory simulations of fluid rock interaction. But I've been involved with CO2 storage, radioactive waste storage, lots of kind of energy-related things. Future potential gas supplies through the use of methane hydrates, and a certain amount of geothermal work as well, and sort of more chemical aspects of monitoring gases in the natural environment. More recently, there's been an increased interest in geothermal energy, both in the UK and abroad. And I'm currently leading two projects, or the UK side of two projects, on two new geothermal programs funded by the EC from the Horizon 2020 program. And we'll have to see what happens over the next couple of years in terms of European funding, but we hope to build upon those and expand. So, roughly what I'll talk about, I'll say something about the heat from the Earth, where it comes from, how it's distributed, some concepts of geothermal systems, and some of the images and that from natural systems. Talk a wee bit about renewability, sustainability, and targets for renewable energies. How we exploit these systems, in particular the heat, other uses of geothermal systems, and then focus a bit on what we've got in the UK in relation to kind of the rest of Europe, and look to the future. Where are we going? What might geothermal energy do in the next decade? And what are some of the challenges associated with that? And I hope this talk will last about 45, 50 minutes, and you can sort of, hopefully there'll be lots of time for questions at the end if you have any. So geothermal, where does the word come from? Two Greek words, there we go, it's the first spanning Greek words, maybe geeks as well, I don't know. Geo meaning of the earth, and therm meaning heat. And it's relating to or utilising heat from the Earth's interior. A similar word is hydrothermal, which is really the hot water, and the hot water helps to move the heat within the geothermal systems. Heat can move by conduction through the rock or by convection through hot water circulation. And the water circulation is primarily what moves most of the heat, certainly in a relatively short time scale. So, a quick primer on where the Earth's heat comes from. The temperature increases with depth, fairly logically, and Alexander von Humboldt, some 200 years ago, made the first measurements of temperature increasing with depth and revealed that it got hotter towards the centre of the Earth. And towards the centre of the Earth, some 6,500 kilometres down, we could be at 6,000 centigrade. Shallower levels, the heat's less, maybe 100 kilometres down, you could be 650 to 1,200 centigrade. At the surface, it's very much cooler. Perhaps 0.1% of the entire Earth is below 100 centigrade. So we live on a really quite small, cool part of the Earth, and the vast majority of the Earth is well over 1,000 centigrade, which is I put less than 1,000 centigrade, it should be greater than 1,000 centigrade, beg your pardon. We live on the thin, cool crust on the outside. The heat is generated primarily nowadays from the decay of radioactive elements. This sort of primordial planetary accretion energy is largely been superseded by this radioactive decay of things like uranium, thorium, potassium. The heat is not distributed uniformly. Plate of the Earth's crust move, plate tectonics, and slow convection within the Earth's mantle moves these around the globe, and that allows the heat to come up in different parts of the surface. So you have different parts of the plates. There's constructive plate margins, say the mid-Atlantic ridges, where new crust is created. Destructive plate margins, where the crust comes together, the plates come together, one body is subducted deep into the Earth, and that releases water, and that helps transfer heat into the overlying rocks. And we also find increased levels of heat, say at hot spots, where molten rock punches up through the crust, like in Hawaii, and also where the crust sort of thins and moves apart to the African Rift Valley. All these different sites and the processes associated with them transfer heat to the surface. So some places happen to be richer than others, and that's where we can really kind of exploit the geothermal energy in a larger way. So if we say have plate tectonics in the very large scale structures for heat distribution, say like in this map of the US, the heat flow map, which is in milliwatts per square meter, I think. So on the east coast of the US, it's relatively cold, low heat flow. Towards the west, where the volcanoes are in the US, we get much higher, those areas in red, higher levels of heat flow. Deep within the Earth, the molten rock, magma, if you like, kind of slowly works its way upwards in these big multi-kilometre scale blobs of molten rock, and they bring the heat up relatively close to the surface and power volcanoes. But the way the heat's got to get up will depend on how thick the crust is, the thermal conductivity of the rock, and how groundwater moves. So it's very variable in different parts of the world. So if we say pick the system which might be heated by magma, the molten rock at depth, so it might be 3 to 10 kilometers deep, will warm the overlying rocks, and at some point those warm rocks will have groundwater move through them, and that will start transporting that heat. So it's thermal conduction through the rocks, which may be impermeable, and then this pointer will work on that screen, not really. So the heat will kind of rise up here, and then it'll get to aquifers containing the water, and that will start convecting and bringing the heat up quite rapidly. And we'll see things like hot springs, mud pools, geysers, that sort of thing. If the water comes out, it needs recharging. So further away, the rain on the hills will recharge the aquifers slowly with water, and that completes the cycle. So evidence at the surface, the types of things that we might see. On the top left, you might see geysers, that one's from Yellowstone. You'll see mineral precipitates. Alicia might recognize the sulfur, because we saw that one in Tuscany the other year in Italy. We see mineral terraces, like you find in New Zealand or Turkey. On the top right, you might see steaming gas vents, fumaroles. You certainly don't want to put your feet in those because they can be very, very hot. And either where the geothermal activity is active or has been active in the past, we see a lot of rock alteration. The minerals in the rocks change, releasing the elements, we create lots of clays and the iron oxides, giving this white or this ochreous colours to hillsides. And again, that's in Italy. The natural heat we exploit. We've been exploiting it for an awfully long time. The Romans are very keen on their spa baths in Italy, and they brought that knowledge to the UK when they came here. So the Roman baths in Bath have got hot water at about 45 centigrade from a spring that comes from rocks about 2.5 kilometres deep. We've got some a little closer in Matlock Bath, a bit cooler, mind you, but again, there's been baths made from that. But we're not the only creatures in the world to make use of warm water. Monkeys in Japan are kind of keen, or varieties of them are keen to sit in the hot pools when the weather's cold. And even in Yellowstone in the US, the buffalo will go and, will go and stand next to the warm pools in the winter because it is just slightly warmer compared to the very cold conditions of the rest of the park. However, we only really began to exploit them in some sort of, if you like, sort of modern way in the mid-1800s or the early 1800s in Italy, a place now called Larderello, where a Francois de Larderel, who happened to be a Frenchman, invented a way of extracting boric acid from geothermal waters and geothermal muds, using the steam to drive off the boric acid. He made these kind of domes, these umbrellas over the hot springs, and extracted the chemicals from that. Subsequently, as that was known as an area of heat, in about 1904, a very simple little steam compressor was built, connected to a little generator, and it lit for the first time 5 light bulbs. That was the first generation of geothermal power, geothermal electricity from the system. And subsequently, about 7 years later, they put a small geothermal power plant there, and that stayed there as the only one in the world for the best part of 50 years before the exploitation of geothermal started to take off in places like New Zealand and California. But we use an awful lot of energy on this planet that we live. We light up the night sky, we have lots of modern appliances, and it's mainly powered by fossil fuels. And our renewable energy obligations, or our obligations to reducing CO2 emissions, which underpin global warming, means that we've got to think about different ways of generating power, clean power. That could include nuclear, because it doesn't emit much CO2, but renewable energy technologies are going to have to start taking over. And maybe we'll see the sunset on our conventional Ratcliffe-on-Soar type power stations emitting lots and lots of CO2. But hopefully, with modern technology, we can do better than like 5 light bulbs from a geothermal power plant. So, not a lot of words, I'm afraid, but it's just to describe the renewable energy targets that we have in the UK and Europe. Europe's got a Renewable Energy Directive, and we have to meet some rather stringent targets, or we've signed up to meeting some rather stringent targets, of at least 20% of Europe's total energy needs by 2020. That's spread across a whole range of different countries, and the national targets vary country by country. So I think Malta's only got about 10%. Sweden, I think, is nearly 50% because it has a lot of hydroelectric power. For the UK, we're looking at about 15% as our target by 2020. Although Europe is at about 16% renewables now, and will probably reach its 20% target. It's 50-50 whether the UK will reach its target by 2020. But in the UK, we have other things as well. We've got a low carbon transition plan, which also mentions renewable energies targets, 30% for electricity, 20% for heat, 10% for fuels. Of course, if we have an average number of 20% or 15%, whatever it is, we can't get all that renewable fuel. So other areas have to be larger, hence 30% for electricity. We also have other acts that are relevant, which include cuts in greenhouse gases, phasing out fossil fuels, bringing in new energy supplies, be that solar, geothermal, or wind. So I think by, was it 2050, we went to be 80% reductions in CO2, which is an enormous reduction given how we're sort of on fossil fuels. So how sustainable would a geothermal power plant be? Given that the molten rocks will stay underground and the heat will stay underground for many thousands of years, that looks pretty good. It's going to last a long time. The energy is available 24/7. And unlike other renewable sources, it's independent of the sun and the wind, seasons and tidal cycles, that makes it sound really, really good. It, however, has other limitations. It's limited to certain areas of geography. If you need a volcano, you can't kind of move it. That heat source is going to be under the volcano. You've then got to transport the energy from there to the cities or whatever where it's needed. To drill boreholes can be quite expensive. You've got high upfront costs, make a big investment, and it takes a long time to pay that back. So again, that's another important consideration. We've also got water, which is needed to remove the heat. And you have to maintain suitable amounts of water flow. If you have too much flow, you might cool down parts of your system, you produce less power. So you may have to, if you haven't got much water, re-inject that water to help maintain pressure in the system, help maintain temperatures in the system. Equally, you've got to try and prevent things like scaling, mineral precipitation, which might stir up your pipelines, reduce flow rates, cause scales on the turbines, which would stop you generating power. So it needs to be managed sensibly and carefully. So in terms of impact, what impact would geothermal power have? Well, because it emits less CO2, it's far more environmentally friendly than using fossil fuels. Towards the bottom right there, the amount of CO2 produced in grams per kilowatt hour of electricity generated. Geothermal, it's maybe 13 to 380 grams, compared to coal-fired systems which are over 1,000 grams per kilowatt hour of electricity generated. So just by way of that, Ratcliffe-on-Soar, our local power station, 8 to 10 million tonnes of CO2 a year. It's one of Europe's top 20 emitters of CO2. That's 600 tonnes of CO2 an hour. So by the time I finish my talk, 500 tonnes of CO2 will have been added to the local atmosphere, which is kind of frightening. Geothermal hopefully will be better than that, but it does have some impacts on the environment. You've got to construct the wells, you've got to construct the pipelines. That gives local surface disruption. You go to central Italy or parts of Iceland, you'll see big silver pipelines snaking across the landscape. But once those things are built, there's no sort of noise, it's just really the pipelines and the plant that sit there. The geothermal fluids, though, do contain other gases. They contain CO2, hydrogen sulfide, you get a smell of rotten eggs around the plant, and other lovely gases like hydrogen fluoride, hydrogen chloride, which can make conditions quite acidic. So you may have to treat those or inject them with wastewater. The wastewater, however, is often saline and warm. You can't just discharge that to a river. It might damage the river, it might kill the fish. Chemical and thermal pollution. Some of the rivers in Central America I've seen, they're white with geothermal precipitates, as well as being warm. Even though it's nice to swim in them, in Iceland, for example, they're nice and warm, they may not be very good for fish. So we might have to re-inject those fluids into the water, or if you're by the sea, sort of take them out to sea to dispose of. So where might we find geothermal plants worldwide? A lot of them are distributed where there's volcanoes, so that's around the Pacific Rim of Fire, Western US, Japan, Indonesia, New Zealand. But also we have the Mediterranean, Italy, Turkey, through Central Europe, and then through the middle of Africa, where the rift valleys. And of course, places like Iceland, these island hotspots. I've circled in red some of the bigger producers. It's a rather old map in terms of absolute numbers, but the countries which still produce most geothermal power are still the same. That's the US, Mexico, Italy, Indonesia, Philippines. And there's a whole load of other countries which produce quite large amounts of energy, such as Japan, which can be very, very important locally if you don't have any other indigenous sources of energy supply. So in about 2014, the worldwide use of geothermal energy, it's about 12 gigawatts capacity. So that's kind of 6 Ratcliffe-on-source power stations of energy being produced, with plans to maybe take that up to 16 gigawatts by 2020. And that energy is produced in at least 24 countries in terms of electrical energy, with many more just using the heat from the hot water, such as in heating houses, maybe 72 countries for those. I circle in green Costa Rica for one specific reason, partly because I did my PhD there, it's a really nice place, but also because it is nearly 100% powered by renewable electricity. It's got a lot of hydroelectric schemes, not too many people, and quite a lot of geothermal power. And it's right on the edge of being 100% renewables all the time. I think it's been about 3 or 4 months continuously renewably powered. So it's right at the leading edge of these things. And I think it's roughly about 20% of the country's power comes from geothermal and 80% or nearly 80% from hydroelectric. So it is possible to switch to renewably powered countries. Again, this is rather an old diagram, but it's just to really influence, it's from the early 2000s, but just to show how direct use of heat is much more extensive than power generation. So on the left, you have geothermal power, mainly coming from Italy in terms of electrical power. And that was about 1,200 megawatts of electrical power. Whereas direct use, which is using the heat, it was more like 14,000 megawatts of power. And again, Iceland is there with Italy, but places like Sweden extracting a lot of heat, probably ground source heat pumps, to warm their houses in the winters. Speaking of Europe and the various countries that might produce the power, we have places, like I mentioned, so Italy, Lardarello. We've got places, Izmir in Turkey. We've got a whole swath of areas through Central Europe, in France and in Germany. Some places in Sweden. Iceland, and obviously. Strangely enough, in the UK, we also have geothermal sources of heat, which have been utilised for some years now already, and more are likely to come. I'll show you some of the UK ones in a moment. Now, how are we going to actually sort of applications for this? How are we going to exploit this geothermal energy? We could have, and I'll show you some examples after this. We've got direct use at lower temperatures, which is heating things, drying, de-icing, agriculture, raising fish. We've got warm water for space and district heating, the ground source heat pumps you can use, and directly from low enthalpy waters. If you go in the houses in Reykjavik, most of the heating of the houses comes from the hot water which comes straight out of the ground from a relatively shallow aquifer at about 100 centigrade underneath the city of Reykjavik. Going to the highest temperatures, we have electricity generation either directly from steam, which powers turbines, or binary plants where the hot water heats an organic liquid which is flashed to vapour, and that powers the turbines. So ground source heat pumps, kind of a very brief mention of these. I don't want to get into technicalities, but these could be employed at quite small scale, be it domestic use or sort of business. And it can be kind of one of three ways. You can have an open loop, which is essentially a well or a deep borehole, where you just suck the warm water out, goes to a heat exchanger in the house, and the water is kind of re-injected into the ground. We can have a series of in the middle picture, a series of boreholes down which a pipe is put to extract the heat from those. Or, as is more common, and you see in some people's houses these days in the UK, coils of pipe, plastic pipe, just buried 3 to 6 feet underground in the gardens to extract small amounts of heat there. Another benefit of these type of systems is that in the winter, because the ground is going to be warmer than the air, so you can extract heat. In the summer, the opposite can be true, and the air outside can be a lot warmer than the ground, and you can use them for cooling as well as heating, which in some parts, for example London, we have big office blocks, lots of computers and electrical infrastructure. You may want to cool more than you may want to heat. So it's another important and interesting aspect of these kind of heat pumps. So how do they work? Well, on the right-hand side of the diagram, I don't know if you can kind of read it very well, but you might have a coil of tubes buried in the ground in the garden. Water will be pumped through those, which will go through a heat exchanger and a heat pump, which concentrates that heat, and then sends into the house a secondary circuit, which could be just sort of underfloor heating to gently warm the rooms at about 40 centigrade, or be diverted into a hot water tank and boiler and boost the temperature up to 60, 70 centigrade using radiators in the house. And in doing so, it saves you energy in terms of heating that water up. Another important thing we have in the UK in particular are these what we call lower enthalpy, lower energy, if you like, lower temperature resources. And these may be less than 100 centigrade, but it's sandstones that are full of water. And if we drill boreholes 2 or 3 kilometres down, in the UK having a geothermal gradient of about 30 degrees centigrade per kilometre, you can quite easily get to 60, 70 centigrade in these deep basins. And we know that water, say the sandstones and that surround Nottingham, water quite easily passes through these rocks, and you can extract that warm water. And it's a porous, permeable rocks that you do that. You could either use them for space heating directly, or if they happen to be quite warm, produce power, electrical energy, through a binary cycle plant. So a couple of days ago, I was at Keele University. They happened to have a borehole on their campus, which is nearly a kilometre deep, and they're thinking of using that to heat some of the buildings on their campus directly to save them energy. They're lucky, the borehole already exists, they'd have to pay for that being put in. The binary cycle plant, in its kind of simplest description, you will have 2 boreholes in the ground, you have some sort of hot reservoir at the bottom, you suck the water out, put it through a heat exchanger, and then re-inject the water, the cooled water, and then the heat exchanger warms some organic liquid, potentially butane or pentane, which vaporizes, powers the turbine to give you energy, and then it's condensed and the cycle repeats. If you're lucky enough to have higher temperatures, then you can use the hot water or the steam directly. So this is more your sort of typical power plant that you might see in volcanic areas, say Iceland, Italy, New Zealand. It either uses dry steam, you drill down, extract the steam straight down pipes into turbines, or you get high pressure water, which is well above 100 centigrade, and you flash that to steam. It's like taking the lid off your pressure cooker. You know, you get masses of steam really, really quickly, and that's what powers the power plant. So a good example is Larderello in Italy, where obviously years ago they didn't have much, do you remember that picture? Didn't have much thought about health and safety, sitting next to what would sound like a rocket probably going off when they took top of the well. Nowadays you'll see nice covered pipes ducting the steam to the plant. On the right hand side there's the power plant in the background, and a kind of an exhibition, if you like, of a turbine where the steam will go in on the left, turn the turbine blades, which here are painted red. On the right hand side, nearly out of shot, is the generator, which is connected to that turbine. And that's how they generate the power. So conventional geothermal, it's kind of similar to what I showed previously, but without the organic liquids. There's 2 boreholes, a hot one comes up the pipe, it's flashed to steam, the steam drives the turbine, there's always some wastewater produced, and that is recombined with a condensed steam and either re-injected or goes off to heating uses. In Iceland it would heat houses, for example. It's worth pointing out, in case you've never kind of thought about it or come across it, that the boiling point of water varies with pressure. And so in geothermal systems, it's quite common to have water at 200 or 300 centigrade that only exists as water because it's deep underground. And you often measure the temperature in geothermal wells, and it tracks the boiling point of water with depth. And so at the surface, hopefully you can see this, at the surface here, 1 atmosphere pressure, it will be 100 centigrade. But as you go deeper, and on this rough sketch, that's a kilometre, that's 2 kilometres, as you go deeper, the boiling point goes up. And so perhaps you might get, on this diagram, my blue line's at about 270 centigrade. That's going to be 600-700 metres down. And that head of water is enough to stop it boiling. This is how your pressure cooker works. And if you suck that water straight up a pipe and keep the pressure right, and then decompress it to the surface, it'll flash the steam straight away. Unfortunately, if it's carrying dissolved minerals, it also precipitates those out. That can cause you problems of scaling of wells and things like that. Now, this is great. You can have very high temperature water, but only so far. If you keep adding heat in, if the rocks are very, very hot, slowly you'll push the water to higher and higher temperatures until you reach a rather magical and interesting chemical point, which is around here, which for pure water is 374 centigrade and 221 bar pressure, which is the critical point of water. And beyond that, there's no water, there's no steam, just a supercritical fluid. It's a kooky area of chemistry, and very, very interesting and very powerful fluids. I'll mention those a little bit more later on. Just to mention now, though, if the water is salty, the critical point moves to higher temperatures and higher pressures. So the energy that you can get out of these systems, the temperatures you can achieve, is dependent on depths, the temperature input, and the bulk chemistry of these fluids. So sometimes, though, we have systems where there's not much water, and we have to kind of help the system in terms of getting its energy out. So if rocks are hot, for example 200 centigrade, but dry, then we can create an engineered or enhanced geothermal systems. These used to be called hot dry rock systems as well. Basically, we use the injection of water down one borehole as an artificial heat transfer medium. So we would drill a well, or drill 2 wells, we inject water down one. We may have to fracture that rock, and there's various ways of doing that. This is what we call hydraulic stimulation, and with a certain amount of pressure, you can cause old fractures to just jog a little bit and improve the fluid flow through them. Or we could create completely new fractures, which is hydrofracturing, which is fracking, friendly fracking in this case, shall we say, and that will connect the one borehole with the other and allow the fluid that moves between them to pick up heat en route. It requires a large rock volume and sufficient pathways between the wells. It needs to be sustainable so it doesn't cool down too quickly, so you don't want really fast pathways, but you can't lose the water. If you're pumping down lots of water and it disappears, then that is a bit of a problem. And that's one of the problems we had in Cornwall 20, 30 years ago at the hot dry rock project there. They were losing the water they were putting in, and they weren't getting enough returns. A slight variant of that, and one which is a bit closer to my heart, is combining this engineered geothermal system with the extraction of metals. One of the problems is the engineered geothermal systems is they're marginally financially viable. So can you improve the economics of them by extracting metals from the geothermal waters at the same time as energy? If you can, you'll get more uptake of renewable geothermal energy. And if you can extract metals that are very valuable, strategically important, then even better. So I'm involved, in fact, I'm leading the UK side of a project which is to do with combined heat, power and metals, CHPM, which is a multi-partner EC Horizon 2020 project, where we're looking at creating engineered geothermal systems in mineral deposits. And as part of that, us at the BGS are looking at Cornwall as our example system to look at. It's long been a major centre of mineralisation, but with the granites and the residual heat from radioactive decay in those, we can extract geothermal energy as well. So the only difference is that on this system, it's circled in red, would be the recovery of metals from the fluids, be it by electrolytic processes or electroprecipitation. And we're looking at ways to try and focus on the more valuable metals. We don't want tons and tons of iron oxide dropping out. We prefer copper or zinc or niobium or whatever, or rare earth elements, things that are going to be particularly valuable. So that's ongoing, and that project's going to run for another 3 years. So if we think about the UK in particular, what can we do in the UK? What things have we got where we can extract energy, geothermal energy? Shallow heat, and the ground source heat pumps. You may have seen in people's gardens, if people have got new houses and they want to get these systems in, lots of pipes being put into the ground. My parents-in-law, their next door neighbours just had one put in. You dig a big hole, put the pipes in, circulate the fluids, and they have a unit in the house, which is the heat exchanger. And this could be particularly useful to provide a base load gentle warming in houses, although, as I mentioned previously, in central London, there's perhaps more demand for cooling in some of the large buildings, and use the local rocks, the chalk in this case, as a heat sink. One issue may be regulation, especially if you go and either access heat or put heat in deeper down, is that who owns the heat? You know, you could, if you extract heat from your neighbours, underneath your neighbour's house, are you stealing their heat or giving them extra heat that they don't want? There's perhaps a bit of regulation needs to be looked at, but by and large, it's a positive thing. If it's very shallow in the garden, then that's not so much of an issue. We do, however, have deeper resources in the UK. So in the left-hand figure, that's milliwatts per square metre, which is the heat flow signature. And we have down in Cornwall, nice bright reds, giving high heat flow, and the Weardale granite underneath northern England, which are high heat flow areas. And these were investigated particularly in the 1980s, and the UK had a big geothermal program. But they're not the only resources. On the diagram on the right, which is a little fuzzy, I'm afraid, but there are large sedimentary basins which contain sandstones, which contain lots of hot water, and they're quite deep. And so there's some in the south of England, up through the Midlands, and then on the northeast, and of course some in Scotland as well. And these are good areas, potentially, where we can extract energy from. Unfortunately, the work was done in the 80s, when we had so much data, and so there's a lot of inferences have to be made about exactly how much heat is there. We really need a new program to re-look at these areas in the light of a lot of the new data that's available nowadays. But the heat flow data for places like the southwest of England suggests that perhaps 5 kilometres deep, it could be 200 centigrade. So that's quite usable usable temperatures if we can get there. So in terms of the sedimentary basins first, if we go focusing on these a little bit, if we need to get hold of the brine from them, we have to drill deep boreholes 2 or 3 kilometres down into these areas, and there are boreholes in all these areas. The Eastern England Basin along the coast, the Wessex Basin down around close to Southampton and the Lower Purbeck. There's a nice deep basin underneath Worcester, which is potentially quite useful for Worcester. There's the Cheshire Basin, quite high temperatures there, it's over 80 centigrade. In places there, unfortunately, there's no towns nearby to use it. And there's basins in Northern Ireland as well. So good geothermal resources, but they have to be somewhere where you could use the energy. And the Wessex Basin is at the moment the one which is perhaps most likely to or is being exploited. So again, the colours represent the temperatures. In red, it's about 100 centigrade, and in blues, the darker blues, it's more like about 35 centigrade. And you can see a big red bullseye just inland from, I think it's Plymouth, there it is, but it's away from the major cities. However, on the right-hand side, circled in red, is Southampton, and the temperatures pick up there to about 70 centigrade, or just over 70 centigrade. And a deep geothermal well was drilled there in the 1980s to explore for temperatures and see what they were in this basin. And what was set up after that, the well was developed by Southampton City Council, and brine at about mid-70s centigrade from about 2 kilometres down, comes up to near the surface, and then it's pumped, goes through a heat exchanger, and is used to heat office buildings in Southampton. So it's quite feasible to do. In fact, there they use the warm water, combine it with a combined heat and power unit, and boost the temperatures even further. And they get about 30 gigawatts of thermal heat per year, of which about 18% is geothermal. If I remember right, though, the well was paid for by the geothermal program rather than this commercial project, and that kind of helped shift the economics of the whole process rather a lot. We do have in Cornwall, though, the potential for hot dry rock technology, and this involves pumping water into fractures in granite. And in the Rosemanoa's test site near Penryn in the 1980s, 3 deep boreholes were drilled. They still exist as a test facility rather than as an energy generating station. They went down 2.5 kilometres, got to about 100 centigrade. They had some success at the time, but it just wasn't quite commercially viable. They achieved fluid flow between the wells, and they got enhanced permeability. The old fractures sheared rather than creating too many new ones. They could connect all these up. Unfortunately, there was a few fast pathways which dominated the flow, and that cooled that local areas of rock down, and they got less power out. And then the pumping costs of the water were quite high. They were losing too much water deeper into the earth. They couldn't contain it all. It was nearly there, but not quite. However, things may be about to change. There's still considerable thermal potential in Cornwall. Circled on the diagram, it says the Carmenellis granite, and you may or not be able to see, but the little blob next to it is the granite itself, and at the bottom right of that is where the Rosemanoa's quarry was. The other granites, at about 5 kilometres depth, they're all kind of thought to have a temperature of about 200 centigrade. So there's a move on to restart the hot dry rock program in Cornwall. I'm part of it. It requires European regional development funds, which exist, and negotiations are in place to try and have a new program of drilling and power generation for geothermal energy in Cornwall. Hopefully, everybody will know more next year. We'll have to see how it goes. These negotiations to go through first. So watch this space. So yes, the UK could have its proper own geothermal power station, which would be rather nice. Okay, the last few slides, I think, well, let's have a think about what future does hold for geothermal. What are the new advances we need to consider? What are the researchy angles that are kind of not being looked at? Where are we going? And I think one of these major areas is super hot systems. So this is going above the critical point of water. We're looking at 400 to 600 centigrade, seriously hot systems. Investigations are ongoing, places like California, Iceland, Italy, Japan, and Mexico. I'm involved with a project which will start in about 6 weeks, where we're looking at a system in Mexico for this. I'm involved with one where we're looking at systems in Iceland as well. There are some really, really major challenges to overcome with this, as you'll see on the next few slides. These include a range of geological factors, like how do you visualize the subsurface? How can you use geophysics to tell you what's down there? Because it becomes extremely important in terms of targeting where you put your wells. Because you're going to have to drill next to magma chambers, molten rock, which causes you a few problems if you drill into it. You've got to understand how the heat is released from crystallizing magma. And then, how on earth does water move in these systems for a whole range of reasons, when really it shouldn't be moving down there, but it is. And then how do these different zones within the systems link together? So taking a few of these, I'll talk about some of the issues at a moment, but could this represent a potential geothermal future, magma energy? Okay, a little link to Monty Python if you like that. There's the Holy Grail. This is the Holy Grail of geothermal energy production. It potentially could be very big. Potentially, because of the way the energies in supercritical water, supercritical fluids are exchanged, you could get 10 times the energy per borehole compared to conventional geothermal energy. That is pretty huge in terms of energy supply. So what is a superhot? Why does it differ to more conventional geothermal? Well, in Iceland, they started up the Iceland Deep Drilling Project. So here's my little simple sketch of a geothermal system. You've got a magma at the bottom. Normal geothermal wells go down maybe 2 kilometres. But the Iceland Deep Drilling Project, IDDP, decided it wanted to seek a really deep well, go much, much deeper into this 400 plus centigrade region where supercritical fluids existed, way beyond the critical point of water. That was the plan. And they chose the the Krafla geothermal power station in northern Iceland to sink this deep well. Power company Landsvirkjun were very much involved. And they're producing about, or I mean, they had 60 megawatts of power at the power station. They thought, great, we can produce more power if we've got access to these very hot temperatures. We know something about the geology. Geophysics says 4 kilometers down there's the magma. We'll be right, we'll drill near that and we'll see what happens. So that's what they set out to do. This diagram shows that where conventional geothermal energy is produced, this sort of boiling point of water in the tops of 2 kilometers, they wanted to go right much deeper, 4 kilometers down, beyond that little sea, which is the critical point of water, into these supercritical conditions, this 400 to 600 centigrade thing. So the first proper well, IDDP-1, it's called, was set at Krafla. The next well they're about to drill is somewhere near the main international airport on the Reykjanes Peninsula, just outside Keflavik in Iceland. So the IDDP-1 borehole, it was rather interesting in what it did. They found its bottom hole temperature was about 900 centigrade when they drilled it, because they hit molten rock at just over 2 kilometers rather than hot rock as they expected. When eventually they got the drilling equipment out of the well and set it onto flow, they got 450 centigrade steam come out to the top. Both those are records in terms of drilling. And that well produced about 100 megawatts of thermal energy, which is equivalent to about 30 megawatts of electrical energy from a single well. That's enough energy for about 60,000 houses in Iceland. It should be noted that Icelandic houses use less electricity here because their heating comes from hot water, which is almost free in Iceland. The wells perhaps could be made slightly bigger in the future, and they're looking at 50 megawatts of electrical energy per well, per borehole, for these supercritical systems. That is absolutely enormous, because the entire Icelandic population only consume around 150 megawatts of electricity for their domestic use. So 3 of these wells could provide all the houses in Iceland empty. That's a population of, Coventry. So that's pretty amazing. So the well was never put on to generate power because it was so damaged after they set about using it. There's a picture of it there on the right. It's in its little shed. It destroyed the insides of the well and both the valves on the top. It had that much energy and that much heat. The system just could not cope with it. In the end, they had to kind of kill the well. But this is very, very relevant to the UK. You may or may not have seen in the papers over the past couple of years, there's been various articles talking about laying a cable between northern England, or northern UK, and Iceland to export power from their geothermal power stations. It'd be a very long interconnector, about 3 times longer than any subsea cable yet made. But National Grid are in serious talks about that, and it could provide a power station's worth of electrical energy from Iceland, in the same way that the interconnectors to France provide us with electricity from France. So IDDP-1 well, they drilled it, they had a great time, they went down 2 kilometers, everything was fine, and then in a very, very interesting 50-meter section, all hell broke loose. They were drilling the well, and when they're drilling wells, they pump fluid down the middle of the borehole tube, and then it brings up fluid on the outside with chips of rock and all the rubbish that they're generating from the drill bit, and it removes the heat. And they suddenly found that all the water started just disappearing into the ground. They just got no returns. No samples came back. It was just disappearing. Huge permeability underground. They drilled a little bit further, and then the drill rate started to go up. They were drilling through something very, very soft. The torque went up, so they were drilling through something sticky. The temperature started to go up. It was quite hot. And then instead of the whole drill string weighing 100 tons, it suddenly started weighing 50 tons because something was kind of pushing back, which had taken some of the weight off the drill string. And they drilled into it 3 times before they realized what they were doing. And then realized they'd hit molten rock in a relatively small zone of about 30 to 40 meters. The system went from about 370 centigrade to 800 or 900 centigrade. And yet water was obviously flowing in these systems. Very unusual. Conventional wisdom would have said, once you heat rock up above 500 centigrade, it's kind of become ductile and you won't get fractures. They will seal up. You can't get fluid flow. And yet, the IDDP-1 well, there's obviously lots of fluid flow. Geochemical evidence from ancient systems that are now exposed, if we sample those isotopically or mineralogically, we can also see there was a lot of fluid flow really close to molten rock. So how on earth do you get the physical properties of the rock to allow you fractures in these systems? We don't really know. And that's one reason why we want to go back and sample this and drill into the magma chamber again and core these last few 50 metres and find out what on earth is going on in this system. What they did do with the well, though, was after they had finished removing the stuck drill tube and various bits from the well, is that they prepared it for normal steam production. So let's see what would happen. They knew it was going to be extremely powerful. So instead of putting a normal silencer on, they just put many tons of rock over the end of the pipe to act as what they call the rock muffler, because it was going to come out dangerously noisy and with an awful lot of energy. So they opened the valve, and what they produced was a great big black smoking steamed cloud for about an hour. And what that was that the water had condensed inside the well, and the aggressive, very acidic gases had dissolved the inside of the steel well and was precipitating particulate metal sulfides. And they blew those out. That black smoke is their infrastructure, their well infrastructure, their steel is being dissolved and precipitated. But after about an hour of flushing all this out, it went to dry steam, and they produced a white smoker, if you like, which was superheated steam, very, very powerful. So, because corrosion is an issue, if they ever shut it in, because water will form, they now realise that if they ever generate one of these systems, they will never be able to turn the well off. So they're going to have an industrial plant where they have immediately two fluid flows. So they can shut half the system whilst the other half flows, or vice versa. But the main well they can't shut, because when they tried to shut it in, they killed the well completely. They would normally kill a well by pumping in water. And the temperature changes were so great by pumping in cold water, it literally damaged the equipment and broke the well. So the temperature itself and the energy is not quite a problem. Speaking of energy, it's a little dark, I'm afraid, but you might be able to see the people for scale. 200 metres from the IDDP-1 is where was KG04 well, where there's nothing left but a big crater now, where one night some years ago the well blew out. These systems have huge amounts of energy, and they will destroy themselves unless you're quite very careful. It's a lot of energy in these supercritical fluids. Exactly why it blew out, I'm uncertain, but it's probably tapping this same zone of superheated fluids. I mentioned fluid flow. This will kind of reiterate the point. How do you understand fluid flow and fracture formation around crystallizing magma? The magma is going to stay hot for a very long time. It's molten rock, so yes, it's got a lot of it has a lot of thermal energy with it, but the latent heat involved in crystallization that's released can maintain high temperatures for many, many years. So we're looking at latent heat processes generating that temperature, and then the rock shrinks and cracks. But parts of it are still semi-molten. So how do you hold all the fractures open? Big unknown. And then with the fluid circulation, it's going to dissolve minerals, and they're going to precipitate. And this is the particular area I'm interested in, is how you can get zones of mineral precipitation as water goes from, say, supercritical, really hot, to cooler conditions. We just don't know how it's going to form. But it seems to very, very quickly precipitate zones, isolate different regions where you may have convective flow with one fluid, then a conductive zone, because you've sealed it with minerals, and more convection, very complicated systems. So the BGS is part of something called the Krafla Magma Testbed, where we're trying to get over £10 million to drill a research well in northern Iceland and go to to boldly call where nobody has called before, kind of drill into this magma chamber and extract samples of probably what will be glass when we get them back to the lab. And this will both inform us in terms of volcanic hazards and how caldera systems and volcano systems behave, but also gives a lot of knowledge about how heat is partitioned within these systems, which underpins this magma thermal energy. And so somewhere on that picture, there's me standing next to the little Mount Fuji-like rock muffler with its silica precipitation on top. So I'm pretty much at the end here. So just to round up, we're faced with having to change how we have our energy generating technologies away from what fossil fuels are generating CO2. Geothermal sources could play a really valuable and vital role in that and meet our renewable energy targets. And we underutilise them at the moment. Yes, there's challenges to overcome, both financial and technical, but I'm sure we can do that. But the next generation geothermal is just on the horizon now. In the next few years, I can see very high-powered geothermal systems coming online, producing high-grade electricity in various parts of the world. And if you put interconnectors from places like Iceland, who knows, geothermal electricity could be coming to houses in the UK, close to you, very, very soon. So, that's it. Thank you very much.